See, this is what we wanted to set up, actually thanks to Dr. Atmiyata, postdoctoral there, okay, she has set it up. What we wanted to show that completely elementary laboratory, if you don't have much things in your laboratory, you can still do such experiments, okay. So see, made of completely rudimentary things, a glass column you can get made from any glass blowing shop, with paying couple of 500,000 rupees, you can make one of these. So what are the flexibilities here? So you can vary the length of the column of your porous media, okay, and accordingly also if your column length is fixed, you can maintain different kind of heads, okay. This is gravity driven, as you can see, okay. Experiment was started when? So you can see it has just started to penetrate. This is the top of the bar, and you can see color changing. This is the dispersion front, okay. By the time we finish the class, you will probably see this front has moved here, okay. This is you have to share in the group. I have taken only a few printouts. You see, this is done in the same column. If you look at the if you look at the top plot, that was with 5.2 ml per minute, right. So one can measure here, one can hold a cylinder with a stopwatch, okay, measuring cylinder, and one can measure flow rate, right. With 5.2 ml per minute, you can see complete breakthrough occurs within 2 hours, 120 minutes, right. You can actually use that data for your moment analysis. I will send that file to you, okay. There will be another experiment now going on. This data will also be generated, right. So you will have 2 duplicate data. On the other hand, if you vary the flow rate, it's like effect of velocity, right. The front goes faster. You have seen that. So in 10 ml per minute, you see the complete breakthrough is in 80 minutes. So it's not linear. So with 5 ml per minute, your complete breakthrough and mean is around 45 minutes. Here the mean is around 22 or so, right. So, and second thing is retardation, right. All of you have heard lot of, have seen what retardation does. Now there is one thing to do model. There is another thing here, like retardation in this case itself is a function of pH, okay, and that pH is absent from the model. Your retardation constant is a function of pH. Where do you take into account? The Kd, okay. So in the retardation adsorption isotherm or in the kinetic constant, if you have a non-equilibrium model, okay, then you take into account, like here to make it faster we have done pH of 2, okay. If you raise it to pH 7, look at the last plot, okay, even the concentration was same, so only 25% came out in 7 hours. It was retarded so much just by changing the pH, okay. So that is your effect of adsorption. It can really retard the plume, okay. So basically retardation constant when you do is not just, people who are behind me can hear me, right, okay. If anybody can stop me anytime and question, okay, ask question, okay. So
here the outflow
yes,
is from this point?
No, this is the overflow to make to maintain a constant head, right. So if you want to vary your pooled water, if you are studying infiltration, okay, if you want to vary your pooled water depth, you can vary 1 centimeter, 5 centimeter, 10 centimeter, okay, depending on which one you close, which one you open, right. So in one column you can do multiple experiments, right, with a simple setup like this, okay. And also what do you put in, if that depends on your goal, okay. So in this case we have put in methylene blue. Methylene blue is in this case there is no bacteria, there is no chemical reaction, so it will be a conservative substrate, but reactive because it will adsorb, okay. Whereas in the same column if I put bromide or lithium or strontium, okay, they will neither adsorb nor degrade. So that will be a conservative non-reactive. Okay. Whereas if I add some bacteria here, inject through one of these ports, I can inject some bacteria that degrades methylene blue, then the same methylene blue will become non-conservative reactive. Okay. So basically it depends on your experimental goal, what do you want to do with it, okay, and what do you want to study, and you can generate all sorts of data with just a single setup. Okay. While these columns are good, and while we are at it, so this is a real soil column, right? Okay. So one can make taller also, all right, and you see these ports, you can reasonably, if you put in, if you remove these and put in syringe in each port, okay, syringe with a cup, small lysi cup, okay, you can actually withdraw multi-level samples also from this, okay, by putting in a syringe, drawing it, and then plug. Okay. So you can also get spatial distribution to some extent. Of course, that will not be that you can only get at the center. The wall effect has to go. Okay, there will be a wall effect, right? So you can also do spatial variation in this column using the same ports, right? So one such column actually can serve multiple experiment, multiple types of experiment, okay? Whereas these will be only for when you are exposed to atmosphere. This will not serve, this will neither serve if you have to do an experiment with undisturbed core. What is undisturbed? There is nothing called undisturbed core, by the way, you know, the sheer fact that you are drilling something is disturbed. So there is actually nothing called undisturbed core. What we would use is a reasonably undisturbed core, right? So what happens? So you do a borehole, the casing goes in, right? And when you have to, so there are two kinds of drilling. In one, you just drill, you are not interested in the core. In another case, if you are interested in the core, what happens is you actually seal and complete core comes out, okay? Then you cut into pieces like this, cap it, and transport it into your laboratory, right? Now, what can you do with this? There are 2-3 things that is done. Either you can cut open the core and study the geology, right? So generally one does 2-3 parallel cores. With one does geology. In another, so what you can do now, you can fabricate 2 caps, okay, with nozzles, all right, and that cap with a with simple gasket, okay, either rubber or Teflon coated if it is adsorbing substance, okay, and then once you have this, so the transportation and cutting in the field disturbs this, right? So then what you do in the laboratory, often with cold laser you cut this, the defined section, a fine cut, and then put these 2 caps, okay, and now you can run the experiment using one of the pump attached to one of the point and actually run that experiment, okay, with reasonably, what is called reasonably undisturbed core. Of course, there is nothing called undisturbed core, as you can understand, that because it went in the soil, it compacted the soil a little bit, okay, sideways, right. So that is, so for undisturbed core, things are different. Now what if the undisturbed core came from anaerobic region, something like a sediment of a lake, deep lake, or deep down, 300 meter, 400 meter, right? So then what you need is, in addition to all these, you need something else, okay? So now we are going to move in and show you what else do you need. It's basically, let us say your core came from undisturbed core, capped, came from deep down. You can't open it, because the moment you open it, it gets contaminated with the atmosphere outside, right? So what do you do? So you create an atmosphere which is oxygen free inside, okay? Now this is basically a balloon kind of thing where there are 2 gloves. So inside you can work using these gloves anywhere, okay? Basically 2 gloves you can process, so outside you can see. And what is this? This is the most technical part of this setup, okay? This is a airlock system, 2-way. So when inside door is closed, you open the outside door, okay, what happens? Inside of this compartment is separated from inside, is at the same environment as outside, right? So whatever you have to take in, you take it in, then close this airlock. Then once you start this, what it creates a vacuum, drives out oxygen, fills up with inside gas. So this runs 3-4 cycles until the inside of that is at the same pressure and air composition as inside. Then from inside you can open that door and take it in. Okay? So basically in sealed condition, it goes from outside atmosphere to an atmosphere that is oxygen free. Then you can create your complete experimental setup like inside. You can take everything inside gradually. If there are big things like that, that's an incubator sitting there where you can maintain temperature also. Okay? For those, one can open this and take it in once and then make it oxygen free. Okay? So these kind of setup you need to process such sensitive cores or sensitive materials. Okay? So basically more complex the experiment is, more expensive setups you need. Okay? So but elementary outside experiments like phreatic zone or unsaturated zone or water table aquifer or reasonably where you don't expect anaerobic region, those kind of setup is sufficient. Okay? Okay, so it's a constant head experiment, right?
So Shobhan, it's solid glass beads, right?
Yeah. But silica surface adsorbs methylene group because it's with the OH it's mildly negatively charged. So, but with pH2 we made it almost not adsorbing, but still not totally. Yeah. Yeah. Okay. Any questions so far? No. So let us think of then what do we do? This is all in the lab, but 3D. This morning you have seen the 3D. Finally, the world is three-dimensional. Okay. So what do you do when you go to the field? So field on the surface of the ground, you don't know anything what is going on out inside, right? So now you have to devise things where you can get depth-wise information, right? Horizontal locations at different location, depth selective locations, right? Because if you put a borehole and start pumping, it will get water from entire length. You don't have a depth selective sample. What if I want water sample from 1 meter, 2 meter, 3 meter, 4 meter? How am I going to do that? Okay, at any location. So if something is infiltrating, I can collect depth-wise samples. Okay, or there are many other situations that one can come across, different redox regions, different. Okay, so this is one such setup. Typically, these are, I don't know how many of you heard of Packers? Packers? No? No? Nobody heard of Packers? Okay, wish we had a board here. So this is a Packers system. Okay, typically they are used, earlier they used to be used for estimating hydraulic conductivity of cracks in the rock. Okay, so what is done, say let's say there are multiple cracks in the rock, so you want to plug the cracks, just keep one open and pump that crack. Okay, so how is it done? So same concept, then we modified for sedimentary aquifer. Okay, so what is it? See this is at the bottom. See there is a cone. Okay, so entire setup is like this. This goes at the bottom. On top of that, this goes. Okay, on top of that, this will go. Okay, and this will sit right at the top. So first this, then this. Okay, then this intermediate piece, then this. Now this entire thing actually goes inside the borehole, okay, whichever depth you want, okay, and then from top you can inflate this. This is like a balloon. You can inflate this and plug the top and bottom. So this is at the bottom, this is at the top, in the middle is this. Shall I lay it out for you down there? Yeah? Hey, Anup, aa jao. One of you hold. Hey, ये रोल ना हो जाए, इसको पकड़िए. So एक साइड में ले जाओ. हाँ, एक साइड में ले जाओ. उसके बाद ये लगाओ. Don't have to put it, just lay it out. Okay. Okay. Then take this. Yeah, this better. Only part water can come out when you pump is from here. Okay, because you have plugged the entire rest of it, and on top of it, from top there is no hole for water to get in. So you are just pumping for 6 inches. Okay. So what do? So any borehole has a stored water. So if you pump for some time, what happens? The stored water first gets out. After that, the influence region is barely from 6 inches radiating a little. Okay. So you are going to get a zone of influence cone which is very thin, and you are going to get sample from there. Okay. So this way one can actually collect, and if you analyze that with that only 6-inch thing, you get a zone of influence nearby within the 1 meter. If you collect samples soon enough, within 1 meter it just radiates up to 1 feet or so. So you can actually get a resolution of 2 meter each, with 2 meter completely disjointed, zone of influence. Okay. So you can collect depth profile of every 2 meter, and that is a very fine resolution for the field scale. Okay, using this kind of setup. But in order to use this in a sedimentary aquifer, you need to modify your borehole. What is the modification of borehole? Typically in a borehole you have casing and then filter. In this you need completely filter, and maybe you will be sampling whatever, either contaminant or tracer you inject or whatever. So that might adsorb. So that borehole has to be wrapped with geotextiles. Okay, someone with geotechnic background will understand, right? So you wrap the borehole with geotextiles so that the soil particles don't get in. Okay, but it is non-reactive geotextiles so that all the solutes can get in. Okay, inorganic, non-adsorbing. Okay, and the entire casing is perforated. So then when it goes in anywhere, if you plug the top and bottom, you are basically pumping from that 6-inch. Okay, and you can use the entire depth of the borehole to sample this. Okay, so this was the modification that was done for the sedimentary aquifer, but you can still use this system almost anywhere now. Okay, so these are the kind of system one can use for the field work. Okay, if you have a borehole to sample, you want multi-level sampler, you can use this to collect multi-level sample so that you have a depth resolution. And remember depth moment, once you have a depth resolution, right? Okay, you can use the depth moment to calculate the vertical dispersion for the infiltrating water. Okay? Thanks, Nani. Yes. Yes.
Regarding ORP measurement, once we take out the water and measure, then its condition totally changes. So using this, how can we
what we did is very interesting. So when the water comes out, okay, if you collect it right there, then it's aerated. So what we did is on top of at the exit, we actually put a pipe very high, about 10 meter, I think it was 6 meter pipe. Okay, and near about 1 meter we had a tap. So water that is coming out is exposed to atmosphere at 6 meter, but we are taking the sample right here. Okay, and when we are taking the sample, we already had a nitrogen purging in the tube, right? Nitrogen purger. So as the sample was getting in, we lift the nitrogen paja, so inside environment is nitrogen. So one can design a very simple system. With a single nitrogen cylinder, you can drive this. Anyway, to drive this, you need a nitrogen cylinder. What happens is, to inflate this, we inflate it with water, but deep down it doesn't deflate so easily. So then there is another port through which one can inject nitrogen to drive that water out. Okay, so anyway, to operate this system, you need a nitrogen cylinder, and same thing we can use for. So it's a very simple setup when you think of it. All you need is an extra pipe with a tap. Okay, the water column is rising and getting exposed at the top, and you are collecting sample there, which is virgin water, right? Okay. Any other? And anyway, WRP you cannot trust in the field. The fact is, WRP is a mixed measurement. So when it is collecting sample from different zone in a heterogeneous system, WRP, there may be several zones, maybe nitrate reduction zone, there may be sulfate reduction zone, and water is getting mixed. So you get what the EH you measure, WRP you measure is a mixed. So it's better to actually measure hydrogen. So hydrogen, what you need is a partition setup. So you have a gas phase, inert gas, either helium or nitrogen, and then from the water, hydrogen partitions, and then you can inject and measure with the RGD gas detector, reduction gas detector. Yeah. So hydrogen element, molecular hydrogen will give you exactly what is the redox couple, right? Yeah. Any other questions?
Sir, in that soil column.
Huh. Let's see. Let's come here. Hey Anup, इसको धीरे धीरे ऊपर करो. देखना रोल ना हो जाए, नहीं तो बक्सा के अंदर कर दो, केसिंग के अंदर कर दो. हाँ.
You have used, I think, this 1.5 inch or 2 inch diameter.
What is the diameter? I forgot. 0.3. No, diameter of the column.
Oh, diameter of the column. I thought you were talking about the sand.
No.
This was.
Do you remember?
I can't remember, but I think.
It should be about 5 centimeter, 5 centimeter, 2 inches, 2 inches.
2 inch. So, will the wall effect shall be considered in the
Wall effect will be considered if when your flow rate is very small. If your flow rate is higher, the wall effect will not be that large. Okay.
So, what is the flow rate you are maintaining here?
We can maintain anything from 3 to, because this is so porous. In this we maintain, what was the first experiment? This one, is it? This was the sand?
No, this was the
Glass bead. The sand experiment?
The sand one took more than 6 hours.
More than 6 hours, and it didn't.
Because we didn't start with pH 3,
Right.
we started with the normal pH. So a lot of it got absorbed. The methylene blue got absorbed, so we had to.
So originally I wanted to demonstrate with sand, but sand absorbs too much of methylene blue. You can't actually see your question. I mean, in 6 hours it will just penetrate few millimeter.
It started
Okay.
around 10 ml per minute. That's the flow rate.
So with this has very high hydraulic conductivity. This kind of sand.
And when you pack that soil column, is there any consideration?
See, if you pack it, if you want uniform and no air trap, okay, then what should happen is basically you first fill up with water, okay, then let the sand drop, so that it drops as individual grain. There is no air pocket anywhere. Whereas if you first pack the sand and then try to flow water, there will be residual air pockets, because small pore bodies with even narrower pore throat cannot be penetrated with this much head, right? You need a much better higher head to penetrate that. So you know the pressure saturation curve of unsaturated soil, right? So, okay. So then you have to actually drop the sand, right? Whereas if you want to do unsaturated zone experiment, of course you will first pack the sand and then. Okay. In that case, what you have to do is actually this setup will not work. What you have to attach is with top of this. That's why this ground glass joint. With ground glass, you can completely seal it, right? On top of that, you can make a small nozzle, and then that nozzle you attach to a tank and that tank can be elevated so that you can increase the pressure as high as you want, because that will now be continuously connected. There will be no air. Okay, and you can, because it will be sealed, you can actually apply pressure. Okay, positive pressure. Right, and so you can actually, that is also a simple setup can be constructed using a ground glass joint, because ground glass joint can really be sealed well. Okay. Yes.
The bottom is flat.
Bottom is not flat. We have used glass wool to make it flat. Okay. Ideally, what you would want is a porous. I mean, if I am doing a real porous media experiment, not a demonstration project, I would do a porous glass plate. Okay, a flat porous glass plate is what I would use at the bottom. Okay.
Here also you use that.
Yeah, glass wool. These are glass wool, not
No,
wool,
porous.
but the glass wool. No porous plate. No porous plate. So porous plate we have substituted with a glass wool packing, basically, with a level surface. Okay.
And this breakthrough means the complete.
Yeah. This is the constant inlet concentration. See, this is the outlet concentration. So you can do C by C naught. You can calculate. This will be 1. Right. Okay. So I'll send that data file to all of. I'll send it to Shubham. Shubham will send it. Huh? Shubham, you have the everybody's ID, so you can send them. Okay. So this data will also come out. So we'll send you both the data, right? And see now, almost there, right? Right when we started, it was around here. Now it is almost there. Okay. और 1 घंटे में हो जाएगा ना?
Took 2 hours.
Took 2 hours.
We started
Yeah.
around,
4.
it's been 40 minutes now.
Okay.
I think we should start seeing color fields now.
Then
This is 8.
6th sample, see a little more color, right?
This is 8.
So 8th sample, little denser, right? So this way it
This is
just
the
keeps
input.
going. Yeah.
This is what we have putting in.
This is at the end. Yeah. No, this is the input.
This is the input. So
Input.
basically you can
So by
compare it
12th they were almost there, right? But this will be actually taken reading in the UV visible spectrophotometer, right? So you can't trust your eyes to do that, right? Impossible. So, okay, fine. Any other question? It's just got the color, huh? Third sample already color. Yeah, one can see actually, one can see. It won't be as high, yeah. Okay, thank you. Let's go for tea. Cut. Now I remember.